There is a human species with no face, no reconstruction, no artist's impression based on a skull, no skeleton that reveals a height or a posture or a way of moving through the world. Everything we know about them comes from a fragment of a finger bone the size of a child's fingernail, found in a cave in the Altai Mountains of Siberia in 2008, and from a handful of teeth recovered from the same site in the years that followed. That is the entire physical record of the Denisovans. A finger, some teeth, no face, no body, no art, no tools we can confidently attribute to them. No language, obviously, no culture we can point to, no ruins, no graves we can recognize as theirs. And yet the Denisovans are not gone. They are inside us. Somewhere between 1 and 6% of the DNA of every living person of Melanesian, Papua New Guinean, Aboriginal Australian, or certain Southeast and East Asian ancestry is Denisovan in origin. Not metaphorically, not as a distant echo, as actual functional genetic sequences that have been doing biological work inside living human bodies for 50,000 years, right up to this morning. The people of Tibet breathe at high altitude more efficiently than most populations on Earth because of a gene variant that came from the Denisovans. The immune systems of populations across Southeast Asia carry Denisovan contributions that may still be shaping their response to pathogens today. A species with no face has left its mark inside millions of living people in ways that are measurable, functional, and ongoing, and the full implications of that fact are only beginning to be understood. To understand why this matters, you have to understand how the Denisovans were discovered, because the discovery itself is unlike anything that has happened before in the history of paleoanthropology. Every other human species we know about, Neanderthals, Homo erectus, Homo heidelbergensis, Homo floresiensis, was identified first by its bones. Researchers found a fossil, described its morphology, argued about where it fit in the human family tree, named it, drew reconstructions of what it might have looked like, and built a picture of the species from the physical evidence outward. The process was slow and contentious and filled with debate, but it followed the same basic logic every time. Body first, identity after. The Denisovans reversed this entirely. There were no bones first. There was only DNA. In 2010, Svante Pääbo and his team at the Max Planck Institute for Evolutionary Anthropology extracted genetic material from the finger bone fragment found at Denisova Cave in the Altai Mountains of Siberia and sequenced it with techniques that had only recently become powerful enough to work on material this degraded and this old. What they found was not Homo sapiens. It was not Neanderthal. It was a third kind of human, genetically distinct from both by a margin large enough to place it in its own category, a category that had never been described before in the scientific literature. They named it after the cave where the bone was found because they had nothing else to name it after. No morphology, no reconstruction, no face. The Denisovans entered the scientific record not as bones, but as a sequence of nucleotides, an entity defined entirely by its genome, before a single physical feature was known. This had never happened before in the history of science. A species identified by its genetic signature before anyone knew what it looked like, or where it lived beyond one cave, or how long it had existed, or how it had ended. And what that signature showed, when researchers began comparing it to modern human genomes, was something that changed the entire framework of human evolution as it had been understood for a century. The Denisovans had not simply lived alongside modern humans and then gone extinct. They had interbred with the ancestors of modern humans at some point, probably multiple points, during the period when Homo sapiens was spreading out of Africa and moving through Asia. And the descendants of those encounters, the people carrying Denisovan DNA sequences today, are not obscure isolated populations living at the edge of the human world. They are, in many cases, the populations who reached and populated the most challenging and remote environments on Earth, the people who crossed open ocean to reach Australia and the Pacific Islands, the people who colonized the high-altitude environments of Tibet and the Tibetan Plateau, the people who pushed into the deepest islands of Southeast Asia and built cultures there that have lasted tens of thousands of years. This is the twist that changes everything. The Denisovan genetic contribution is not evenly distributed across the human species. It is concentrated in precisely the populations that accomplished the most extraordinary feats of human expansion and environmental adaptation. And in at least one documented case, the Tibetan case, that concentration is not coincidental. It is functional. The EPS1 gene variant that allows Tibetans to regulate their blood oxygen levels at altitudes that would incapacitate or kill most other humans traces directly to a Denisovan origin. Researchers comparing Tibetan genomes to the Denisovan genome found that this specific variant, which does not appear at meaningful frequency in any other modern human population, matches the Denisovan sequence far more closely than it matches any other human source. The Denisovans lived in Asia for hundreds of thousands of years. They had time, evolutionary time, to adapt to the range of environments they inhabited. When the ancestors of modern Tibetans encountered Denisovans in Central Asia and interbred with them, they acquired, among other things, a genetic tool for surviving at altitude that their own evolutionary history had not yet produced. They did not develop that adaptation from scratch. They inherited it from a species that no longer exists in any other form. This is what makes the Denisovan story unlike any other story in human prehistory. It is not a story about extinction. It is a story about transformation. The Denisovans did not simply die out and leave nothing behind. They were absorbed, genetically, into the populations that replaced them, and in that absorption, they contributed specific biological capabilities that those populations carried forward into environments and challenges that no prior human had ever faced. The finger bone in the cave is not a relic of something lost. It is the visible tip of a contribution that is still, in the most literal biological sense, alive. There is still so much the genetics cannot tell us. We do not know what the Denisovans looked like. Researchers have made tentative predictions from the genome about certain physical features, using a technique that maps epigenetic signatures in ancient DNA to anatomical characteristics. The predictions suggest they may have had wider skulls and wider pelvises than Neanderthals, possibly darker skin, possibly other differences in facial structure. But these are inferences built on inferences, and the margin of uncertainty is large enough that any reconstruction carries more speculation than science. We have no face, we have no voice. We have no record of how they lived, what they ate, how they organized their communities, whether they made art, whether they buried their dead with intention, whether they had language in any form we would recognize, whether they had anything that a modern observer would call culture, a cave in Siberia, some teeth, a finger bone. That is the entire physical record of a human species that existed for hundreds of thousands of years across a range that may have stretched from Siberia to Southeast Asia, from the Tibetan Plateau to the islands of the Pacific margin. We know they lived in Denisova cave alongside Neanderthals at various points, because the DNA of both species appears in the same sediment layers. We know the cave was occupied across an enormous span of time. We know they were there long enough to develop genetic adaptations to specific Asian environments that were sophisticated enough to be useful to the people who inherited them 50,000 years later. And we know that somewhere, at some point, possibly many points across a vast geographic range, they met the ancestors of the people who now live on the other side of the world from that Siberian cave. And that those encounters left marks in those people's genomes that have never faded and are still doing biological work today. The question this raises is larger than one species. If the Denisovans contributed functional genetic sequences that are still doing biological work in living populations today, what does that suggest about the nature of extinction itself? The conventional picture of human prehistory has always involved a series of replacement events. Modern humans spread out of Africa, encountered the species that had been living in Eurasia for hundreds of thousands of years, and replaced them. The Neanderthals disappeared. The Denisovans disappeared. Homo erectus disappeared. The story has always been told as a sequence of endings. But what the genetics are now showing is that disappeared is not quite the right word for any of these endings. A species can be absorbed. Its genome can travel forward inside the genomes of the people who replaced it, carrying specific adaptations, specific immune responses, specific physiological capabilities into environments that the replacing species alone might not have managed. The Neanderthal contribution to modern human immunity has been documented. The Denisovan contribution to Tibetan altitude adaptation has been documented. What else was contributed, in encounters we have not yet identified, in populations whose specific Denisovan signal we have not yet measured? Remains an open question that the expanding database of modern and ancient human genomes is only beginning to answer. Extinction, in this picture, is not always a door closing. Sometimes it is a door opening into a form of persistence that the fossil record alone could never have detected. A persistence written not in stone, but in the living bodies of every person who carries even a fraction of what was passed forward in those ancient encounters. The Denisovans were never simply what we thought they were, which is to say they were never simply gone. They are present in every Tibetan who breathes without difficulty at 4,000 meters above sea level, in every climb, in every breath taken at altitude by a population that carries in its EPAS1 gene a gift from a species that has no other monument. They are present in every Aboriginal Australian whose immune system carries a Denisovan contribution into an encounter with a pathogen today. They are present in the Pacific Islander navigators whose ancestors crossed open ocean to reach islands no prior human had ever stood on, in the specific biological capabilities that may have made those crossings survivable. They are present in ways that the finger bone alone could never have told us, in ways that only the genome can read, in the living biological text of every descendant of every encounter that happened somewhere in Asia. Over a period of tens of thousands of years, when two kinds of human met in a landscape neither of them fully owned and found, for reasons we will probably never fully understand. Reasons that may have had nothing to do with strategy or planning, and everything to do with the ordinary fact of proximity, that the boundary between their kinds was crossable. The data is only beginning to tell us how many times that happened. And what it left behind is still, in the most literal sense possible, alive.